Select the major product of the following reaction. So we can see that we are starting with a ketone. And what we are reacting this with is a primary amine. And this trace amount of acid probably looks a little bit strange to you. That just indicates that this reaction takes place under slightly acidic conditions. So for this reaction, so just slightly acidic is what that means. And for this particular reaction, you can read that as the pH being approximately 4 to 5, so just a little bit below that neutral pH of 7. So it's important this doesn't get too acidic, because when it gets too acidic, you'd have all of your amine in its protonated form and you wouldn't have a nucleophile. So your amine is a nucleophile and the carbonyl of that ketone is your electrophile. So I am going to go through and draw the mechanism for this. Just a warning, it is a long mechanism. But then when I'm done, I'm going to show you the fast way to get to the answer, because you're not always going to want to take the time to draw out every single step. So this primary amine is your nucleophile. We're going to assume we have some of it unprotonated because it's not that acidic, and this is also not acidic enough to protonate that ketone. So this is going to be a neutral nucleophile attacking the neutral ketone. And so that's going to be our first step. And so we will form a tetrahedral intermediate. So oxygen with a negative charge, and we have added the nitrogen to that. And it still has 2 hydrogens, so it has a positive charge, and that's still going to have a bond to its R group, which in this case is the cyclopentane ring. All right, so what makes this mechanism so long is all of the proton transfer steps that we have taking place. Okay, so we want to protonate first this O negative. That's not going to stick around for too long at this pH of 4 to 5. So we're just going to assume that we have some source of acid in here. So I'm just going to say in generic H+. Okay, the most likely species, of course, is probably one of these protonated amines, but we're not going to clutter up the mechanism too much. Okay, and this is all reversible. So let me put these reversible arrows in. Okay, and so we will have protonated that oxygen. So we have OH. And then we still have our nitrogen protonated. These are these proton transfer steps that just make this mechanism so long. All right, and so the next thing that's going to happen is some base that you have in solution. Maybe it's the neutral amine, maybe it's an equivalent of this. I'm just going to say in general, base. So something with a lone pair of electrons can take one of these protons off the nitrogen. So we're really just moving protons around here. Because what I ultimately want to do is I want to set this OH up here as a leaving group. So that's what I'm kind of keeping my eye on as I move these protons around. All right, so this is going to give us a neutral intermediate, because now we don't have a positive charge here. Right, so we get to this neutral intermediate, and then what we want to do ultimately in this reaction, it is an equilibrium, we're going to lose water. So we're trying to set up this oxygen to be lost as water. So I'm going to go ahead and protonate this. So again, I'm just going to say generic H+, but it could be any protonated species that we've encountered along the way. So we have lone pairs of electron on this oxygen, and we're going to protonate this. And so what we're doing is we're trying to make this into a good leaving group. It's slightly acidic, so pushing this off as a hydroxide ion doesn't make sense at this pH. We've got to push it off as a protonated we're going to have to protonate it so we can push it off as a neutral water molecule. Okay, so we're getting there, but I did warn you that it's a very long mechanism. So we have this protonated, and so we've got here now is something that's going to get us to looking much closer to what the actual product is going to be. So what happens here is we've made a good leaving group, and we've got this lone pair of electrons on the nitrogen that can help push that off. So we're going to do this. And so now we're getting to something that looks a lot like the final product. And then I promise I will show you the fast way to get here. And so this nitrogen is still protonated. And again, some base in solution, which could be another equivalent of amine or anything here along the lines that we've encountered that's basic, is going to remove this proton to give us a neutral product, which you can see is this one down here. It's the imine. And so every single step of this mechanism is reversible. So you do this under dry conditions, and if you want to reverse it, you're going to do it under wet conditions because you're releasing also water here, right? So you've also formed some water there, so completely reversible. So the fast way to get to a product, right, is to recognize that wherever you have your ketone oxygen, you're going to form what's known as an imine. So an imine has that is not the right imine that we selected. After all that work, not that one. We have our double bond here. We're looking for this imine. Okay. So what we're going to recognize, and my shorthand trick is what led me to saying that, wait a second, I selected the wrong carbon-nitrogen double bond there. So this nitrogen is basically going to be replacing this oxygen. So you can imagine just kind of snapping that in place with a double bond, and that will allow you to get to the right imine product. And I apologize for the confusion there. If I have time, I will redo this video.